Yeah, so I'm going to be talking about the fundamental forces of nature. And the idea overall is to explore geometric algebra as a language in which to do physics. And the conclusion is that it's extremely useful for physics and enables us to reach quickly advanced areas that other mathematical languages, such as vector analysis, complex analysis, quaternions, matrices, spinors, tensor calculus, a big list. They can only each individually cover whatever area we want to look at partially. And it takes often a lot of time and dedication to get into. You really have to devote, sizable fraction of your life to understanding things like tensor calculus properly. But what I want to do today is take you through to some advanced areas, equipped basically with just the geometric algebra of 4D space, which we call the Spacetime algebra, or STA. And the advanced areas I want to get through to, they'll all be associated with the fundamental forces of nature. So it's an ambitious program, but because of GA and STA, we're going to be able to get to these really quite advanced areas in this single talk. So here's a bit about the 4 fundamental forces of nature. We'll be looking at each. So there's electromagnetism. That's down here on this table at the bottom. That's the easiest one to start with. That's got a range of infinity because the particle which is meant to mediate it, the photon, is massless. The other force which has a hypothetical, it must be said, mediating particle which is massless and therefore has infinite range is gravity. That's extremely weak. And then you have something called the weak force. This governs particle decay and is short range because the particle carriers you see here, the W and Z particles, they are massive, really quite massive. And then finally there's a strong force that binds quarks together, and the thing that binds them are the gluons, and we're going to be looking at those later on. And this is very short range, again, because what's involved is massive. So those are the things we want to look at. Now, how do they work? What's the general sort of principle for these? They work via invariance under groups of symmetries. So we're going to explore these symmetries using the tools of geometric algebra and the STA. And as part of this, I want to explore something that until recently I had thought stood outside the main line of GA development. Now, we know in detail from what's happened so far at this meeting that GA is very good for understanding both complex numbers and quaternions. And you can view complex numbers as the even elements of the GA of 2-dimensional space, and quaternions as the even elements of the GA of 3-dimensional space. This is what they turn out to be. However, you may know that both complex numbers and quaternions are what's called normed division algebras. We'll look at that in more detail, but basically what it comes down to is you can take any 2 elements, each of them has an individual norm, and when you multiply those elements together, you get something that has a new norm, but it's the product of the old ones. And they're division algebras because the only thing that has 0 norm is 0 itself. So you can always find a non-zero norm for everything else. So there's a third such algebra. It's called the octonions. And these haven't been terribly popular historically because they are a pretty strange object. So we know, well, that complex numbers are associative and commutative. So they function just like the real numbers in that sense. Quaternions are at least associative. So AB times C is the same as A times BC. But of course, they're non-commutative. And octonions, however, they're neither associative or commutative. And the lack of associativity looks like it's a really big barrier to using them in physics. But we'll see, in fact, perhaps surprisingly, that they can be represented nicely as even elements of the geometric algebra of 4-dimensional space, the space-time algebra, which are otherwise known as Dirac spinors. So actually, there's quite a neat thing here. We have complex numbers, quaternions, and now the octonions as the even subalgebra of 2, 3, and 4-dimensional space in the geometric algebra approach. So this is very interesting for us as regards fundamental forces, because octonions have recently been used in particle physics to try to express the fundamental symmetry groups in the standard model. And a person called Cole Fury has been spearheading these recent efforts, building upon previous attempts over some decades. And these studies make use of something called chains of octonion multiplications, and these work a bit like a code. They're very clever because they build up things with quite high complexity from very simple building blocks, just like codes. And we're going to be able to start here on a similar analysis using just the STA itself to express these codes. And I just want to say something in the light of what Chris was saying yesterday. Chris was recommending we don't get hung up on merits of particular algebras, but treat them democratically based on uses for particular purposes. Well, what I want to do here, the emphasis here, is on the STA within physics. And I want to use it, or see if it can guide us as to the symmetries which nature uses for the fundamental laws. And the overwhelming good feature of the STA for me is that it's set in 4-dimensional space-time. It comes directly from that. And that's basically something that we can be certain about. In the sense that we only know about 4 dimensions existing. And we know what the metric is. It's either 1, 3, or you can do it in 3, 1. So that is something that is actually there, and hence the geometric algebra of space-time seems a very good place to start on whether we can use the geometric algebra to tell us something about what the symmetries of nature might be. Right, so in case there are people who missed earlier lectures, I'll just give a brief introduction to the GA of 3 dimensions before going on to the STA. And more generally, there's fuller introductions and explanations of the topics here up until about halfway through the talk when we start on the octonions. That's all fresh material in this context. And but the previous talk I gave, which covers electromagnetism and gravity in more detail than we're doing here, it can be found on YouTube at this address. Okay, so this early material, we'll skim over it fairly lightly because you'll almost certainly know all of this. So in 3D, we've got 3 orthonormal basis vectors, E1, E2, E3, square to 1. They have 0 dot product, and they have a wedge product, which gives us a pseudoscalar for 3D space. And the dualization here is that I times any vector gives us a bivector. And there's a nice thing that I squared, this is doing this for complex numbers is probably the first way most people get the idea about what geometric algebra is. You take E1, E2 times E1, E2. Let's do it here with 3 things. And you can use here associativity plus swapping things according to the fact that the dot products are 0 to show that's -1. So you've got a real geometric object that squares to -1, and indeed you find there are many such objects as one carries on, which squares to -1. That means that we seldom have use for complex numbers as such. And it's a theme that will persist right to the end here of trying to see if we can do a good deal of modern physics with no complex numbers, but just the geometric algebra of space-time. So we'll call the highest grade object in the space the pseudoscalar. That's what this I is. And what can we do with this setup in 3D? Well, actually, what happens here is going to work in any dimension. Basically, the things we can do very simply, as you've been seeing a lot about, are reflections. Any vector A can be reflected in a vector n to give A dash is minus NaN. And it may be instructive to just actually work that out to see how occurs that that's the case. The point is that minus NaN, when you expand it out using the rules of the geometric product, it comes down to this, a minus 2 n dot a times n, and that is indeed the way you reflect about a vector n. So reflections, they work straight away. Rotations, as you've heard many times here, 2 reflections form a rotation. If you reflect in unit vectors m and n, you get then m, n, a, n, m. And so the rotor is the bit here that we isolate off to give us something which can carry out a rotation via R reverse. Reversion, it reverses the order of all products in vectors. And because of, let me just go back, and because of R being Mn, R times R reverse is then 1 when M and N are unit vectors. And this works in a space of any dimensional signature and for all grades of objects. So you have an object A of any grade, it goes to RA, R reverse. In 3D, you're used to this rotation being about an axis. What's really happening is, of course, you've just got a bivector here, and you're exponentiating the bivector. In 3D, you can refer that back to an axis via the bivector being I times n, where n is the direction. So that's really all we need to say about 3D, I think. We could just compare with the quaternions. So a quaternion is this thing here, A0 plus A1i plus A2j plus A3k, satisfies this. It actually turns out that they form what we would think of as a left-handed set. It turns out to get these multiplications working correctly, you need I equals IE1, j equals minus IE2, and k equals I3. So there's a minus sign in the middle there. But then you've got them perfectly. So let's go to space-time. We want to construct the geometric algebra as space-time. We know we've got this invariant interval from which we can read off the metric. And to do that, we're going to need 4 vectors, which have the properties here. E0 squared is 1. And for I equals 1, 2, 3, EI squared is minus 1. So we're going with the 1, 3 version of the metric. And here's a summary of that. E mu dot E nu is the diagonal plus, minus, minus, minus for mu 0 to 3, mu and nu. So there's 6 bivectors in the algebra, and they come in 2 types. One of them is the wedge EI wedge E0, where EI is one of these things squares to minus 1. And then you've got those not containing E0, like EI wedge EJ. And for any pair of vectors A and B, you can see quite simply that if they if they have 0 dot product, which means that they anti-commute, you can work out that A wedge B all squared is equal to minus A squared and B squared. So these bivectors are going to have themselves squares that are either minus 1 or plus 1. And in particular, the space-like Euclidean bivectors, they square to minus 1. They're generating actual spatial rotations in a plane. And time-like vectors satisfy this, that they're square to plus 1. And they generate the hyperbolic geometry. And in particular, if we take e to the alpha E1, E0, that's the same as cosh alpha, sine alpha E1, E0. And that is basically going to tell us Lorentz transformations very quickly. Now, we should just say something about the pseudoscalar of the space. We're going to use the same symbol I, and we'll be able to justify doing that in a moment. This is the same symbol as in 3D, but we define it here as E0, E1, E2, E3. It's grade 4, and it turns out that means it reverses to itself. And if you compute the square of it, it's another one of these things that gives you minus 1. And I provides a nice duality between bivectors. It provides a map between bivectors with positive and negative square, as you see here. So if you think of I, E1, E0, that's the same as I times something we're going to call sigma 1 in a moment. That's the same as minus E2, E3. And this, anyway, the sigma 1, which is this type E1, E0, that squares to +1, and the type here squares to -1. So that's why it gives a map of that kind. And you've got 4 vectors, and there are 4 trivectors as well. So we've got E1, E2, E3, which is a dual of E0. So there's 4 things you can take a dual of, and you get 4 trivectors. And I anticommutes with vectors and trivectors in this case, and I always commutes with even-grade objects. That would be a space of any size. Now, it's useful here to settle on a given fixed Cartesian frame of vectors to do your analysis. Think of this as the laboratory frame. I'm going to rename the E mu to be gamma mu, because that is the symbol that would be used if you're doing this via Dirac matrices instead. And when you've done that, you've now got the basic tool. This is what we're going to use throughout for relativistic physics, the STA. So we've got the scalar. We've got 4 vectors we call the gamma mu. We've got 6 bivectors of these 2 different types, gamma mu, wedge gamma nu. Here's the 4 trivectors, and then a pseudoscalar I. And that's the spacetime algebra, or STA. Now, gamma mu dot gamma nu is eta mu nu. Expand out this thing. This is the anticommutator, the gamma nu, which is the same as the dot product. And that equals 2 eta mu nu. And that's the sign that we're dealing with the Dirac matrix algebra directly. That is the defining version of Dirac matrix algebra. But of course here, we're working with vectors, not a set of matrices in isospace. And it may seem obvious to us, having worked at it from this angle, that the gamma mu are vectors, and something satisfying this here makes sense from the point of view of the Clifford algebra and vectors. But it was about 20 or 30 years ago when I started first on this, it was incredibly controversial to point to this and say, these are vectors which are satisfying this, and not just the Dirac matrices. And people basically thought you were mad if you said such a thing. It was quite extraordinary. But anyway, we can see that it really does work, and hope to show you how useful it is. Now, we said think of this as the laboratory frame, or it's basically an inertial frame, and this can tell you how to form a set of relative vectors, and these are space-time areas swept out while moving along the velocity vector of the frame. So here's a gamma I, could be gamma 1, 2, or 3. Think of that as being swept out as time progresses up the gamma naught axis. You get to some new gamma I, and the thing that's swept out is a bivector in this space, gamma I wedge gamma naught, and we call that sigma I, and we'll see why that is so in a moment. These type of things square to +1. And of course, the way we've done it, these are actually space-time bivectors, but they can function as spatial vectors in the frame orthogonal to gamma naught. So what we do is call these relative vectors. The relative bit means relative to the velocity vector of the frame. And what you can do is you can take their dot product. Sigma I dot sigma j, I've written that out fully in terms of the anticommutator, and you get a half into minus gamma I gamma j minus gamma j gamma I, and that is just delta ij. And also, if you did this thing, you took their commutator, which is just here, you find you get epsilon ijk I sigma k, where this is a standard thing from ordinary Cartesian. Epsilon ijk is +1 if it's a positive permutation, -1 otherwise. And of course, these two things here are the defining properties of the Pauli spin matrices. So we've got exactly the same thing happening here. we can think of these as vectors in the space orthogonal to gamma naught, and then we have the Pauli spin matrices being represented by these vectors in exactly the same way as we just had with gammas. Now, a particularly nice feature of this is that if we take sigma 1, sigma 2, sigma 3, which are expressed in terms of the gammas like this, you expand it out, it turns out to give you I. And so the 3D subalgebra shares the same pseudoscalar as space-time, which is very nice. We don't have to have two different symbols for that. So we've got this, therefore, this picture of how the even subalgebra, the STA, sits as a subalgebra, clearly, but sits in this particular relation to the full 4D algebra. So the full 4D algebra contains 8 odd elements, the 4 gamma mu's, the 4 trivectors, and then the rest of it is the even ones, and these come down in this form here to give us the Pauli algebra of 3D. And now the odd things here are the vectors of it, which are the sigma I, viewed from 3D, and the pseudoscalar I, which is odd and viewed in this way in 3D. And so the subalgebra of this that's just even would just be 1 and I sigma I, and that does for us as being the quaternions. Okay, so the next thing we need, if we're going to get further in physics and electromagnetism, we need an additional entity, which is the derivative operator. And we define this via something called the reciprocal frame. This is extremely useful throughout mathematical physics. And what this is if E subscript mu is a frame, the reciprocal frame, E superscript mu, is defined by this. E nu dot E mu is this Kronecker delta, delta mu nu. That's 1 if mu equals nu, 0 otherwise. And note in particular that these are just vectors. They're just like the E mu, but they satisfy this reciprocal relation here. And they, in particular, they don't belong, for example, to a space of 1 forms. You find when you're doing the space-time algebra and geometric algebra generally, that you can understand things written in terms of differential forms, but you don't need separate spaces for them. You can replace them by objects which are just living in exactly the same space that you started with, i.e. the STA. So we can use these reciprocal frames to define the vector differential operator for space-time. That's grad is gamma upstairs mu d by dx mu, and we can write that as gamma mu partial d mu. Now, as a quick encouragement, with just this object, this grad, and the STA, you can basically do all of electromagnetism and quantum mechanics through to electroweak theory without introducing any further new mathematics. And I'll be claiming near the end that that extends all the way through to SU3 and the strong forces. Just a little point here, this is slightly off the main theme, but the definition of grad above, we didn't need to use rectangular coordinates on the orthonormal system gamma mu. Suppose you've got an arbitrary coordinate system, for example, standard polars instead of Cartesian, and then what you do is you let x be the 4D position vector, and you find that the following frames are reciprocal. E downstairs mu is the partial d mu of the position. It turns out then the reciprocal frame is the grad of the nth coordinate. You can show, you might like to try this, that they are indeed reciprocal frames. And then the geometric object grad is given by this E upstairs mu d by d mu in this new system. And that's one extremely useful fact. The other is that the upstairs and downstairs components of any vector are given by dotting your vector A with either E upstairs mu or E downstairs mu. And now, you might think these statements look trivial. They're enough to do everything associated with vector calculus and curvilinear coordinate systems. Just this replaces pages and pages of formulae for curvilinear systems that you'll see in textbooks. So it's a great saving in time and effort. Now, suppose I want to then look at Lorentz transformations in the STA, and suppose I want to do a Lorentz transformation in the x direction with rapidity parameter alpha. And the way we do that, we think in terms of frames normally. E mu goes to E mu dashed, where E mu dashed we can now represent as R E mu R reverse, where R is this hyperbolic rotor that we saw before. We write that as e to the alpha sigma 1 over 2. And basically, we can generalize this to R equals e to the b, where b is any bivector in our algebra. And the same rotor prescription works for Lorentz boosts. These are things that have sigma 1s here, sigmas 1, 2, 3, as well as rotations, in which case you would have an I sigma I. And so is this rotor formulation that provides general Lorentz transformation. It works for any object in the algebra. Any object M, you rotate with M dash is Rm R reverse. This is very simple. You met the Faraday bivector yesterday. That's written as e to the IB. The I here is the pseudoscalar for space-time. And this gives the electromagnetic field strength. And that just transforms to a new frame as RF R reverse. Again, you can find formulae which are pages long in some textbooks for this transformation. And it's all contained in this incredibly simple RF R reverse. Now, what we're going to do now is move off to quantum theory, because I want to get that in place before deriving electromagnetism from it. Okay? We're going to be treating electromagnetism as a gauge theory, and I've chosen to illustrate how gauge theories worked by deriving electromagnetism from invariance of the Dirac equation. So let's go off to quantum theory next. And basically, the algebraic structure of wave mechanics arises very naturally from the geometric algebra of space-time. It allows us to reformulate standard quantum mechanics in a more geometrical way. It also suggests new lines of interpretation. And we're going to start with Pauli spinors. We've mentioned the Pauli matrices already. Now, actually, they're normally thought of as operators on column vectors, as was mentioned this morning. And the column vectors are the things that are thought of as the Pauli spinors. So the Pauli matrices, they're shown here. They're matrix operators, and they act on two-component Pauli spinors like this. We write them as psi 1, psi 2. These are complex quantities, so there's 4 degrees of freedom. Now, in the GA approach, something quite remarkable happens. You can replace both the objects, that is both the operators and the spinors, by elements of the same algebra. And so space-time objects and relations between them can replace all single particle quantum statements, which is quite dramatic. And the crucial aspect you have to understand is how to model the Pauli-Dirac spinors within STA. And for Pauli spinors, they've got 2 complex entries in a column spinor. You put psi 1 is A0 plus IA3, A0 and A3 are 2 constants. You put psi 2 to be minus A2 plus IA1, A0 through A3 real scalars, and then the translation is as shown here, right? So we have this complex thing here, A0 plus IA3 in the top, minus A2 plus IA1 in the bottom. How does that translate through? It's very simple. It's A0 plus AK I sigma k. There's a sum over these k's, right? So there's 3 of those. And just as an illustration, if you have a spin-up state, denote it plus, that just becomes 1. If you have a spin-down state, you get minus I sigma 2, and then you can get anything else by combinations, effectively, of those. But complex combinations, we'll see what you need to do to get a complex version of this within the STA in a moment. Now, the crucial thing to show this all works is to show that the action of the quantum operators, sigma k hat on state psi, has a completely equivalent thing as the in terms of operations on the multivector psi. And here's how it goes. Sigma hat k, so the matrix operating on the state psi, turns out to be the same as the kth sigma on the left, psi, and then a sigma 3 on the right. And you can see that the sigma 3 on the right ensures that sigma k psi sigma 3 always stays in this even subalgebra. So this is, it's double-sided, right? But it preserves the fact that psi is in the even subalgebra. And you can then go ahead and verify the translation procedure is consistent by computation. And here's an example. We act with sigma 1 hat on psi. That permutes things like this. You work out what it translates to. It turns out you can then directly show that sigma 1 psi sigma 3. Okay, so that's a direct computation which verifies this equivalence. Now, I mentioned we need a translation for multiplication by the unit imaginary I. And you can do that by noting that if you multiply the three Pauli matrices together, you get this simple matrix here with just I on the diagonal. So multiplication of both components of psi by I is got by taking the product of these three operators. We can do that. It turns out that gives you psi I with I sigma 3 to the right. Okay, so the role of sort of an uninterpreted complex unit imaginary conventionally is taken over by I sigma 3 to the right. And this is basically, David Hessner's found this originally when he was working on the first versions of all this. And this is sort of stuck ever since as being the way to go about having a representation for the act in ordinary quantum mechanics of multiplying by I. And we'll see that this is basically, this thing here turns out to be the origin of electromagnetism, how this operates on the right and what you can do to make the symmetry of this operation of multiplying by a phase become a local one. Now, we can carry on. We can define other things. Let's take psi reverse. In 3D, that's just a scalar. And you can therefore write psi is rho to the half times r, where r is now a rotor, because then psi reverse, if r reverse is 1, is just rho again. So here we can decompose our psi into a rotor and a scale factor. And so now you can begin to see that these spinners people were working with for many years are simply unnormalized rotors. More things we want to do, Hermitian adjoints. It turns out that corresponds to reversion followed by reflection of the time axis in general. That's what happens in the Dirac case. But the reflection of the time axis, we put a gamma naught each side. The gamma naught passes through the Pauli spinners because they're in the even subalgebra. So in 3D, you've got that the Hermitian conjugate is actually just psi reverse. And you can use that to derive the quantum inner product. It turns out that the bra ket put together here, the psi phi, is equivalent to this Hermitian conjugate psi dagger times phi, and you put these angle brackets around. What does that mean here? We aren't doing a Bra-Kent notation. This is just a standard way of representing the scalar part of a quantity in geometric algebra. So you take the scalar part of psi dagger phi, and then you multiply by I sigma 3 on the right, and take the scalar part of that, multiply by I sigma 3, and that's a full translation for the inner product in terms of the STA. So this view, it offers a number of insights. It transforms your view about ordinary quantum mechanics. One can suddenly see what's going on in ordinary quantum mechanics with things like spin precession, things like that, and various ways in which people are using the observables corresponding with spin, you can now see them coming straight out of this rotor approach in an incredibly simple way. But you could have a look at the previous game talk for some examples of that in the 3D case. What we're going to do now is jump straight to the 4D case in Dirac wave functions. And really, we haven't got too much new to do to deal with Dirac theory. So this is the relativistic theory of spin half particles. And it's very simple. The Dirac wave function now consists of all elements of the even subalgebra of the STA. And so it turns out that when we do that, the wave function is no longer a weighted spatial rotor. It's now a weighted function times a full Lorentz spinner. So here is our psi. We now have 8 components corresponding to the 8 even elements in the STA. And you can always write that as rho to the half, rho is just an ordinary scalar, just like before, times the rho to r, which is now a full Lorentz spinner. And then you get an additional thing, which is e to the I beta over 2, written like that. Beta is a scalar. And so you have a sort of duality rotation coming in via this I factor here. And it must be said, I don't think David Hessner's believes he's ever got to the bottom of what this factor here means. It does seem to be related to antiparticle states, and we can, of course, use it perfectly well in all our computations, but having a feeling as to what it means that's comparable to, say, the rho being the scaling and the r being a rotor, that's basically still for someone to work out, I think. So the main new thing we need to do to make all this work is to establish what the action of the Dirac gamma matrices are on a state psi. So we want to know what gamma mu hat, where that's a matrix, translates to. And here's the answer. It's double-sided again. We now get gamma mu on the left, that's one of our STA vectors, times psi times gamma naught. And the gamma naught on the right keeps this in the even subalgebra. It turns out that the imaginary is the same as in the Pauli case. It's still I sigma 3 to the right. That persists all the way through. And now you can start forming observables, and these are things that basically are bilinear operations on the psi. The most useful one of them all is what we call J, the direct current. That's formed by psi, gamma naught, psi reverse. If you take that form of psi we had just now, in terms of the rho e to the I beta r, then you'll see that this thing here, because I should say I anti-communicates with gamma naught, but reverses to itself, try it out, put psi equal to psi times e to the I beta over 2, you'll see that you lose that mysterious e to the I beta factor completely, and you just get that J is rho times R gamma naught R reverse. Exactly the same thing happens for transforming gamma 3. We think of that as a spin vector, and that's rho gamma 3 R reverse. And we get this quite nice picture, which is very similar to rigid body mechanics, of how you start off with your fiducial gamma vectors. Psi then transforms these to the observable J equals rho V, the spin vector S, and then 2 more things, and these represent phase. They get rotated round by phase changes I sigma 3. Now, there's our wave function. What is the equation it obeys? And it's incredibly simple. This is the form first proposed by David Hessner. This is for free space. And you get grad psi I sigma 3 to the right is m psi gamma naught. And it'd be hard to think of anything simpler that you could write down. That's obviously got to combine the geometric algebra grad, just here, the geometric algebra psi, and bring in the mass m. Anyway, that is the equation. That is the full Dirac equation in free space. And if you now form the divergence of J and use the J as psi gamma naught psi reverse, then you're going to get terms in grad psi. You use what grad psi is from this equation just here. It's minus m psi I gamma 3 when you move that over the other side. And it turns out then that you can quickly find you get 0. So the divergence of J is 0, the current J is conserved, and that has the implication that fermions cannot be created or destroyed. And basically, pair annihilation and production are high-energy multiparticle processes. They're not covered by the Dirac equation in this form, right? So everything I'm talking about in regard to quantum mechanics here is all at what they call the first quantized level. To cover these sort of processes, you'd have to go to second quantized systems, which we believe you could do via a multi-particle version of the Dirac equation, but we never got through to the end of that in terms of having a fully working system. And that's still to be done. Now, something I want to help emphasize here is that the time-like component of J is positive definite. So explicitly, if you use later, I want you to see that gamma naught dot J is gamma naught psi reverse. I put it in this angle bracket thing to indicate taking the scalar part. And it's the sum of 8 squares, and the 8 squares are the coefficients that we introduced earlier to describe the state. Okay, so gamma naught dot J is an sum of 8 squares. And it's clearly positive. That's a key thing there. It's interpreted as a probability density, and a normalized wave function has that the sum over space of J naught is 1. And conservation of J then means that you can think of probability density flowing along non-intersecting streamlines. And I'll do this very quickly, but I know some of you will have seen this before. This is the first, this is a first application of this particular apparatus that we've built up so far to visualizing what's going on in a quantum so-called measurement. What we're going to look at very briefly is Stern-Gerlach apparatus. This is where you've got a field in this direction, particles passing through it, electrons passing through it, for example, well, something which has spin, and it is separated out into spin-up and spin-down components. And in the traditional view, what you're doing is measuring. The view we would have via the development so far is that the apparatus acts as a spin polarizer, forcing the spins to align with the magnetic shock of going through this region. And this shows a case with an initial wave packet, which is a Gaussian in the z direction. It gets split into these two packets here, and you can see the streamlines, again, show this splitting, they bifurcate. But the key thing is this one, which is for the spins. The spins are all in the x direction when they go in. They get churned up by the magnetic fields, but then as they spread out from the apparatus, they all gradually turn into either completely up or completely down. So you've generated a spin up or spin down bifurcation, but you've done it in this sort of rather causal, deterministic way. So where does the randomness come in? That comes in where in the wave packet a particular streamline is seeded. One's near one side of it will go one way, one's near the other side of it will go the other way. And so you replace questions about collapsal wave functions, things of that kind, by asking, well, what's the initial data you have? And once you've got presumably randomized initial data, that can feed through to the end of the process to give you the standard quantum mechanical predictions, but you've been able to maintain a causal deterministic picture throughout of what is happening.